So in today's lecture, I would like to talk about one of the most interesting examples of Kac-Moody Lie algebras, which is Affine Lie algebras. Of course, the first example is simple Lie algebras themselves. And but what's beyond simple and what's well studied is affine Lie algebras. So let us give a couple of definitions first. As always, we denote by G. So let G be some Lie algebra, a Lie algebra. And for us, it's not even important if it's finite dimensional, infinite dimensional. So let us define what's called a 2K cycle on G. A 2K cycle on G is a bilinear map it goes, so let's call it psi. It goes from G times G to C, and it satisfies the following property. So it is satisfying first of all, it's antisymmetric, so psi of pair x, y is negative psi of yx. And also, it satisfies property that we will need for Jacobi identity. And that's why it's called K-cycle. So psi of x, y, z plus psi of y, z, x plus psi of zx, y equals to 0. Okay, so such thing we call a 2K cycle. And so let us fix some 2K cycle on G. And so let psi be 2K cycle on G. And let me introduce a new Lie algebra. As a vector space, so this new Lie algebra will be denoted as G with tilde. And as a vector space, it is G, and I add one more element and call this element C. Okay. And I introduce Lie bracket on such a vector space as follows. Of course, we have Lie bracket on G, and I extend it to G tilde by the following rule. X plus lambda C. So this is some general element in G tilde. I commute with y plus mu C. By definition, I put that it is a bracket of x and y, and plus our K-cycle times C. So claim that this defines a Lie algebra structure on G tilde. And G tilde as a Lie algebra is called central extension of G by 2 co-cycle psi. So let us formulate it as a definition. So Lie algebra G tilde is called a central extension of G. Okay, so we will need another construction to define affine Lie algebras, and this construction is called adjoining derivation to a Lie algebra. So let us fix some derivation on G. So let D, it is a linear map from G to G, be a derivation on G. It means that it acts on a commutator by a Leibniz rule. So it is dx commutator with y plus x commutator with dy. Again, I define new vector space. Let me call it, guess, G prime. It is G plus I add one more element and call it D. Okay. And I introduce a bracket on G prime. So I say that, okay, x plus lambda d and y plus mu d, such thing, it is just a commutator of x, y, plus lambda d of y minus mu d of x. Okay, so it's a good exercise to check that if d is derivation, that such a bracket satisfies properties of being a Lie bracket. So it is antisymmetric. Of course, it's antisymmetric and satisfies Jacobi identity. So this defines a Lie algebra structure on G prime. And such, we will say, just some terminology, that we say G prime is obtained from G by adjoining a derivation, adjoining the derivation D. So this is how we call this construction, adjoining a derivation. And important example of derivation for us will be when our Lie algebra G is graded. So suppose G is graded. What does it mean? It means that it is a direct sum of some subspaces. They are labeled by some indices. Well, in our case, we can just take these indices to run over integers, say, or over all positive integers. What's important is that how Lie bracket behaves under this decomposition. If I take gi and commute with gj, this gives me all elements of such thing will be in gi plus j. So this is by definition, then we will say that G is a graded Lie algebra. And then if I define the following linear map, D of x is some j times x, where j is a degree of x. Meaning that when I say j is degree of x, it means that x belongs to gj. So I claim that such a linear map, of course, I define it only on what's called homogeneous elements, which belong to each subspaces. But of course, by linearity, I can define this as a linear map on G. And the claim is that such D is a derivation, and I cannot join it to make a new Lie algebra G prime. So then D is a derivation. Okay, so now we are ready to define what is an affine Lie algebra, but we start with what's called loop algebra. Introduce loop algebra. By definition, it's a Lie algebra, and as a vector space, well, we write just denote this new vector space in the following way, and it is our G tensor product with all polynomials in variable t and t inverse. So why it is called loop algebra? Because you can think of it as a G-valued polynomials on a circle, and circle is also a loop. Okay, and I need to introduce what how a bracket on this vector space. So I commute x tensor t to the power I with y tensor t to the power j as follows. So they say commutator is pointwise. So I just take a bracket of x and y, tensor it with t to the power I plus j. So this is my definition of loop algebra. Well, it's an easy check that it is actually Lie algebra, and this bracket satisfies all the needed properties. I will also need to define residue function. Residue function. Let's call it like this. Let's write res for residue function. It's a function from g t inverse. So our goal now is to construct some Tuka cycle on loop algebra. So that's what we're doing now. So this is a map from here to complex numbers, and I just take so this is an element here is a sum of some powers of t with some coefficients and finite sum. And I take this and see what is the coefficient for t inverse and this is my value of res. Okay. Okay, also let me fix, so suppose that my algebra G is such that it has a symmetric invariant bilinear form on it. So let, by this parenthesis, we denote symmetric. So let this be symmetric bilinear form on G. At the end of the day, G will be just simple algebra, so you can take this to be killing form, for example. So let's formulate a lemma. I take psi AB to be the following. It is residue of the following two elements. Derivative of A with respect to T. Derivative here is clear what it is, right? Because, well, it just, you can define derivative, usual derivative of polynomials with respect to T. This is pretty algebraic operation. And so that's what I am taking here and with B. So such thing is a Tuka cycle on G on the loop algebra. Okay, proof is just straightforward. You just take and check all the properties that we need for psi to be a Tuka cycle. So straightforward. I will leave it as an exercise. So let's move on. On the other hand, so then we can apply our constructions that we introduced. We can take loop algebra and consider central extension corresponding to this Tuka cycle. So let G prime of T inverse be the central extension of G with Tuka cycle psi that I introduced in this lemma. Then I can also say that G prime T inverse is graded. Okay, so what is the grading? Okay, let me put it on board. G prime of T inverse, our central extension, is graded by the following rule. So we just say that degree of such element x tensor t to the power j is j. And also I need to say what's the degree of the central element that I introduced by when I centrally extended the loop algebra. So it is just 0. Okay, so what you need to check, and actually it's obvious, right? So if you commute so first of all, it's a basis, right? And then when you commute two elements, two homogeneous elements which have degree by this definition, then I get something in the corresponding homogeneous element, right, with degree I plus j, if I commuted two elements of degrees I and j respectively, right? Okay, and so finally I define affine Lie algebras to be the following: affine Lie algebra. It is denoted as G hat, and it is as a vector spaces loop algebra, right? Then I add central element, then I add adjoining derivation. So is the Lie is the Lie algebra obtained from the central extension of the loop algebra by adjoining the derivation that we got when we introduced the grading on G prime. So d of a equals to ja, where degree of a is j. Okay, so these are the main heroes of today's lecture, and they are very important for modern physics, for conformal field theory, for example. And so that's why people would like to see what are the representations of such things. But what we would like to see today, at least to some glimpse of it, is why this has a structure which is similar to structure of simple Lie algebras that we learned in this course. So it is because these are Kac-Moody Lie algebras. And to see that, well, I just picked one example, one like simplest example that you can get, but it's informative because, like, if you understand this example, then more or less you can understand how this example generalizes to all affine Lie algebras. So my example is the following. Consider generalized Cartan matrix the following. A, it is 2 by 2. It has 2 diagonals, as all generalized Cartan matrices should have. And then I have negative 2's on off diagonals. So this Cartan matrix is degenerate. So therefore it cannot be Cartan matrix of any simple Lie algebra already. So we already have something new. And the theorem that I would like to prove, because it's we'll see construction how everything works, is that Kac-Moody Lie algebra corresponding to this generalized Cartan matrix is isomorphic to affine SL2. Right? So in all our constructions that we introduced, take G to be simple Lie algebra, SL2. The form that we had there is a Killing form. And the construction that we have gives us G hat, which is SL2 hat in this case. So I claim that this is Kac-Moody Lie algebras with such generalized Cartan matrix. Okay, so let's start proving this, but we'll see a lot of additional constructions on the way to prove. Okay, so I said that you can take killing form, but rather maybe I can also take a multiple of killing form, and in my case I would like to take the trace form. So take xy to be trace of xy. So xy are some matrices, 2 by 2 matrices, so they are elements of SL2. Okay. All right. So this is the form that I fix for the rest of the proof. And then also let me recall my usual standard notation. We have E, F, and H. This is standard basis. A basis in SL2. Okay. Okay. So now let me denote by Gothic H the following three-dimensional vector space. It's a vector space with basis H. This is an element of SL2. Then the second element of the basis is our central element when we centrally extend, and D. So this is H. So what I'm doing now is I'm constructing minimal realization of the Cartan matrix that I introduce. So in minimal realization, I need to give you what? A vector space, and moreover, this vector space should be of some particular dimension. So if you remember, so my A is 2 by 2 matrix, right? So therefore, dimension of H so should be, so remember we had formula 2n minus rank of A. So rank of A, it's a degenerate, and you can compute it. It's 1 in this case. N is this size of matrix, so this is 2. So it's 2 times 2 minus 1. So 4 minus 1 is 3. So I need to give you three-dimensional vector space. That's what I'm giving you. Aside of this vector space, I need to give you set linearly independent subset of vectors in H of size 2, of size n, right? So I need to give you two elements. In previous lecture, we have the following numeration H1 and H2, but I would rather label them as follows: H1 and H0. So H0 will be C minus H. So it's an element in this vector space. And H1 is H. And this will be our usual rule for today. What is labeled with 1 corresponds to just usual Lie algebra, simple Lie algebra, SL2. So H1 is just usual H. What's labeled with 0 is something additional. So this additional thing we have because we, for example, added central element. Okay. Aside from these two elements in H, I'll also need to give you two elements of linear independent elements in H star. So define alpha 0 and alpha 1. So these are elements these are linear functionals on H. So they live in H star as follows. So of course I need the following to make it realization of A. So value of alpha I on Hj is Aji. So this is the Aji. These are elements of the matrix A, right? So let me write it like this. And I and J, they are well, from 0 to 1, right? They are either 0 or 1, right? So 0, 0 element is the first element of the matrix. 1 is the second element of this matrix. So that's how it's. So maybe let me even write it explicitly. So I have A0, 0, A1, 1, A0, 1, A 1, 0, like this. Okay, but this does not fix me elements alpha 0, alpha 1. We have values on two linearly independent elements of H, but we need values on all elements of H. So I also need to give you how is it evaluated, say, and to one additional element, say D. So alpha 0 of D, let me put it to be 1, and alpha 1 of D is 0. Okay. So this fixes me alpha 0 and alpha 1. And so let me also write a couple of values of alpha 0, alpha 1 from the definition of H0, H1 and the values of Cartan matrix. You can deduce that alpha 0 acting on evaluated on central element as well as alpha 1 evaluated at central element is just 0. So this is just consequence of this and this, but this is just definition of alpha 0 and alpha 1. Okay, so then I claim that H, then pi, which is H0, H1, this set, and pi check, which is alpha 0, alpha 1. So this triple is a minimal realization of A. Yes. So it is obvious that it's minimalization. The one additional thing that we never spell out is that alpha 0 and alpha 1 should be linearly independent. But this is because of this condition, of course. Okay. So to now I need to move towards realizing why SL2 hat, affine SL2, is affine Lie algebra. So is Kac-Moody Lie algebra. Sorry. So in Kac-Moody Lie algebra, remember we had these generators, Chevalier generators, EIs and FIs and HIs. Well, HIs we already have, and I need to introduce AIs and FIs. So set the following notation. As I said, what is labeled with 1 will correspond to just usual SL2. So E1 is E and F1 is F. But what about E0 and F0? Okay, so right. So these are elements so this E1 FR1 should be elements of SL2 hat, right? By the way, maybe I need to. Okay, so let me first introduce E0. So let me finish writing formulas, and then we'll discuss it. So E0 is F tensor T, and F0 is E tensor T inverse. Okay, so these are elements. So these are all elements of so EI, FI. They are elements of SL2 hat. So remember that SL2 hat was a central extension of SL2 of a loop algebra, which is given by SL2, right? In loop algebra, we have an element of the Lie algebra which is under the hat times some power of t, and this power may be negative. So this is clear why this E0 and F0 are elements of SL2 hat. What about E1, F1? There's no tensor with a power. So whenever I don't write tensor with a power, I think that it is E tensor with T0. And similarly, F is just, I think of it as an element of SL2 hat as F tensor T0. So I think of SL2 as a subalgebra in SL2 hat corresponding to the 0 power of T. Okay. Okay, so as I said, E1, F1, they are just our usual generators for SL2. For E0, F0, something is happening very interesting. For example, they should be generators, so therefore they should generate all powers, positive powers and negative powers of T. So therefore, it's kind of clear why E0 should contain T and F0 should contain T inverse. But then but then roles of F and E switched. So E0 contains F in it, and F0 contains E in it. So this is something interesting. Okay, so now I introduced all the objects. Now let us make a plan how we use them to prove the isomorphism that we want to prove. So we need to check the following. First of all, that well, these generators, we don't know yet that they generators, but at least we would like to see that they have so EI, FI, and H satisfy the relations from, let me write it like this, L of A tilde. So remember, when we introduced Kac-Moody Lie algebras, before quotiening by the maximal ideal which intersects trivially with H, we introduced as L of A tilde by generators and relations. And so I would like this to satisfy similar relations. Second thing that we would like to have in our agenda is let us have, we would like to check that they are really generators. So EI, FI, and H generate the whole Lie algebra SL2 hat. And the third part, third item is that we would like to see that in SL2 hat, there are no ideals, say J, such that J intersects H trivially. So intersection is just 0. So I claim that if we check these three things, we prove the theorem. Why is that? So 1 and 2 will mean that we have surjective homomorphism of Lie algebras. Let's call it phi tilde. This is from L of A tilde, right, to SL2 hat. But then 3 says that the ideal, maximal ideal, which intersects trivially with H in LA, that we quotient by, under phi tilde goes to 0. So this condition. So therefore 3 means that will mean that we have surjective homomorphism, not from L tilde now, but from L of A, from the Kac-Moody Lie algebra, corresponding to the matrix A. So to SL2 hat. So the question will be then, what is, so if we call this homomorphism phi, so the question will be, what is the kernel of phi? But here, we can deduce easily, just from the construction of L of A, that the kernel of phi is 0. So first of all, let me first consider phi tilde. So what's the kernel of phi tilde restricted to H? And this is H, not from SL2 hat. I'm kind of abusing notation here, but H that we introduced in as the generators in L of A. And also in the lectures we had H tilde, right? But again, I am double abusing notation. So this H is the H that lives in L of A tilde. So just need to go to the previous lectures to see what is this thing. So I claim that this actually is 0, just because of our construction, right? So actually F tilde maps H, or H tilde if you wish, to this H in SL2 hat, right? And this H in L of A has dimension 3 or less, right? Because it's just a minimal realization, mod sum maybe relations, but the image is 3-dimensional. So so therefore phi tilde restricted to H is an isomorphism. Okay, but when I quotient by the ideal, which intersects trivially with H, right? I never, so I still have kernel equal to 0, right? When I quotient by this ideal, I don't change anything, and so I can just remove phi tilde from here. So this. But this just means that kernel of phi, it's an ideal in L of A, and it intersects trivially with H. But since it intersects trivially with H by construction of L of A, right? In L of A, we actually quotient, what was the construction? We quotient L tilde of A by the maximal ideal which intersects trivially with H. So therefore, there are no non-zero ideals in L of A, which intersects trivially with H. So from this, we can deduce that kernel of phi is actually 0. But this means that this phi, it is injective, not only surjective, but injective, and it is isomorphism. Okay, so I hope that I convinced everybody that if we check these three things in our agenda, then we prove the theorem. So now let's start checking. So, to check one, well, we have a bunch of relations. So check item 1. So I need to check some relations for EI, FI, and H. You can just do them all at home. It's semi-interesting exercise, but useful. I don't want to do it all on the board now. I just pick one which is the most interesting. First of all, you need to to have some formula for psi, for the Tuka cycle. So if you go through all these definitions that we gave today, then the Tuka cycle evaluated at the following two elements, y tensor t to the power j. The formula is the following. It is I and then x, y. So this is our trace form, if you remember. Or 0. And this is, so this is if I equals to, so if I plus j equals to 0, and this is otherwise. So this is the formula for our Tuka cycle. And using this formula, I would like to give you just one check, an interesting one. So I would like to compute what is E0, F0. So the question is whether it gives or not H0. So let's check this. Okay, let's check. So I get E0, F0. Let's recall what they are. So E0 is the rows of in-left switch. So F tensor T with E tensor T inverse. Okay, then according to the definition of central extension, it is the commutator of F and E tensor T 1 plus negative 1, so 0 here, plus well, we need psi of E0 F0 C, right? So therefore, and psi of E0 F0, it is, according to the formula that I gave you, is actually F E, the trace form of F and E, all right? Because E0 is this one, F0 is this one. 1 plus negative 1 is 0, so therefore this Tuka cycle is not 0, so it's given by 1 times the form, right? So this thing is trace of matrix corresponding to F times matrix corresponding to E, and you can compute that it is actually 1. What is this? So we agreed that tensor T0 is just, by abusing of notation, is just F with E. And F with E gives me negative H. So what I get is C minus H. And this is exactly our definition of H0. Okay. So we got one of the relations, and the rest of them I would like to skip, and but it's a good exercise to check them all. So let's now end with part 1 of our checking list. So let's check part 2. So we need to prove that that EI, FI, and H, they actually generate SL2 hat in sense of Lie algebra, right? If I start doing more and more brackets, then I will get everything. So let me denote by M. So let M be a Lie algebra or Lie subalgebra of SL2 hat generated by EI, FI, and H, like all the elements in H. So I take all possible commutators with this, with all possible sets of elements from this set, and I call this M. This is of course Lie subalgebra in SL2 hat. So our goal is to see that M equals SL2 hat. Then we will prove part 2. Very well. We will do it by induction. So we will prove by induction. By induction on K. That SL2 tensor T to the K belongs to M for each K. If we will do that, then of course we will prove that M equals SL2 hat, because, well, in SL2 hat we have all elements of this sort, and plus also C and plus D. But C and D, they already belong in H, right? So therefore we prove that everything in SL2 hat is inside M. But since M is the subalgebra of SL2 hat, then they just equal. Okay, so base of induction of course you can take K equals to 0, but then this with the step of induction that I have, this base will not work. So I need to take K equals 1. Very well, and I define the following set in SL2. So these are all elements, not in SL2, but in SL2 hat as a subalgebra in SL2, such that X tensor T, just in the first power, belong to M. I would like to see that it is a non-zero ideal in SL2, therefore it belongs to SL2, therefore it coincides with SL2. Okay, so why it's not 0? Because, say, f tensor t, this is our E0. And E0 is inside M, of course, because it's M was generated by EIs. So this belongs to I. So therefore F so E0 belongs to M. So therefore F belongs to I, right? So therefore I is not 0 already, right? So therefore F is inside I. So therefore I is not 0. Okay, so I need to check that it is an ideal. I take x from I and y from SL2. Just x is also from SL2, but it's also from I. But y is any element from SL2. And then I take, I consider, then I would like to take commutator and see that this thing is inside, it belongs to M, right? Well, this I can write as follows. X tensor T with Y. So we know, since X is in I, we know that this belongs to M. And Y also belongs to M, because it's an element of SL2, right? So therefore, the whole thing belongs to M. So therefore, X, commutator of X and Y is in I. So therefore, I is an ideal. And as I said, then I equals to SL2. So therefore, base is checked. Okay. Okay. Step is actually even easier to prove. Well, I take Z tensor Tk, right, from SL2 tensor Tk. Well, since SL2 is simple Lie algebra, any element is belongs to the commutant, and we can actually, without by linearity, assume that Z is actually a commutator of two things, right? Therefore, Z tensor Tk is, I can write it as X tensor T, Y tensor T K minus 1. Right? So we know that this thing belongs to SL2, belongs to M. А как стереть вот это? Бумага. So we know that X tensor T belongs to M, and that this also belongs to M. This is by induction assumption. This is by base, actually. And therefore, the whole thing belongs to M. And the step is proved. OK, so we proved part 2 of our checklist. And now the most interesting is 3, actually. So to check 3, we study root decomposition of SL2 hat. Root decomposition in what sense? That actually, well, in the usual sense that we all used to during the semester, we just know that SL2 hat, it has subalgebra H, commutative subalgebra, finite dimensional subalgebra H inside, and therefore SL2 hat is a representation of this subalgebra decomposes into direct sum of corresponding weight subspaces that we denote as G lambda, where lambda runs over H star. Yes, so G lambda here, G lambda, sorry, is just our usual weight subspace. So this is all elements X from SL2 hat, right? Such that the commutator of H with this X is just lambda of H times X for every H from H. Okay. So the question is, for which lambda G lambda is not 0. Such lambda are called roots, and the corresponding decompositions then called root decomposition. And it will coincide with the root decomposition of this as a Kac-Moody Lie algebra. Okay, so I claim, let me introduce one more element of H star. We already had alpha 0, alpha 1. So let me define delta, an element of H star, by the following. So evaluated H at H0 and evaluated at H1, it just gives me 0. But evaluated at D, it gives me 1. So this is the most important role of the element D that I added. So sometimes in the applications, people even forget about this D, but this D is important if you would like to see that my affine Lie algebra is Kac-Moody Lie algebra. Okay, so I claim that if I take the vector E tensor Tk and consider subspace spanned by this vector, then this will be exactly the root, the weight subspace corresponding to alpha 1 plus k delta. And then C of F tensor Tk will be G negative alpha 1 plus k delta. And then if I consider weight subspace, which is spanned by, well, H tensor Tk, this H is just usual H. It's not a subspace, it's an element, it's from standard basis of SL2. This is G k delta. Okay, So how to see that? Well, we just can use commutation relation to see that this subspace is inside corresponding weight subspace. But equalities follows from the root weight decomposition there. Okay, so what? So we can, for example, check so we can call this 1, this is 2, this is 3. So how to check 1, for example? Well, you use commutation relations. So you take, for example, H1, right, and commute with E tensor Tk. And you shall see that this is alpha 1 of H1 plus K delta of H1. So this is, all this is a number, times E tensor Tk. So this is 0, right? This thing, alpha 1 of H1 is 2, right? So this is actually, so what you need to, so what I wrote here is a statement, right? So this is what you need to check, right? But why is that true? So what's written, so maybe I put a question mark here. So delta of H1 is 0. This is 2. And so therefore this is just, so what's written on the right hand side is just 2E tensor Tk. Right? But how do I compute? I compute commutator H1 with E tensor Tk. Right? So this thing is H1 E tensor Tk. All right. Plus maybe something that some multiple of central element, but this multiple is 0 because k here and 0 here, right? So therefore the whole thing is just this, but the commutator of H1 and E, and H1 is just H, right, is 2E. And so there indeed this equals to this. And so therefore we proved question mark. Then we need to check this with H0 and with D. So the interesting case is with D. So alpha 1 of D is just 0, and delta of D is 1, right? But on the other hand, the commutator of D with E tensor Tk just multiply this E tensor Tk by the degree k. And this is exactly k here. So maybe let me do this computation, since it's interesting. Okay. So let's do this computation. So D with E tensor T to the k. So by, again, if you trace all the definitions, so this D, like commutation with D, acts exactly as a derivation that we adjoined. And our derivation, if you remember, acting on this vector just gives me the degree of this vector. The degree of this vector is k. So therefore, commuting of the D with such vector is just k times E tensor Tk. On the other hand, I would like to see that this k is exactly alpha 1 of D plus k delta of D. right? E tensor tk. So, and this is true because this thing is 0. This is how alpha 1x on D we saw earlier. Delta of D is 1. So we have k times 1. This is exactly this k. And so this is how it works. Very well. So I checked that E tensor tk is inside G alpha 1 plus k delta. But you can, in the same way, you can check that, say, these inclusions. So in our claim we have equalities here, right? But you can, using commutation relations, instead of equalities, you can check inclusions. But then if at least one of this inclusion is proper, right, then you don't have, this is contradiction to weight decomposition. You don't have enough vectors, you know, to satisfy this weight decomposition. So it's a standard argument which says that checking this inclusion is actually enough. So this is actually equality, and the claim follows. Okay, again, I didn't write all the formulas, but we'll stuck in here for a while if I'll check. So I just gave a couple of interesting examples. Okay, so therefore, the root system, therefore we know what is the root system of SL2 hat. It is plus or minus alpha 1 plus k delta and L delta. So here k runs over all integers, and L runs over all integers except 0. So this is a root system of SL2 hat. Okay, so now, what was our task in the beginning? To see there are no ideals intersecting trivially with H. Okay, so by the sake of contradiction, let us consider such an ideal. So let I be a non-zero ideal such that I intersects H trivially. Then, okay, SL2 hat the representation of H is has weight decomposition, and I as an ideal is a sub-representation, and we know that any submodule, any sub-representation also admits weight decomposition in this case. This is from one of the problems of seminar. So therefore, so let me put it on board. I also admits weight decomposition. So it means that we have actually at least one weight vector. So at least one element of G lambda, where lambda is from this set, right? So therefore, but we know all weight vectors actually, right? So therefore, I should contain an element of this form. For some I from Z, and here X may equal E, F, or H. Right. So these are all possible weight vectors. So since I has at least one, so let us consider this one. It is of this form, X under Ti, where X is one of these elements, E, F, or H. These are elements of SL2, our standard elements of SL2. Okay, so now take Y to be, depending on what is X, let me take Y, F, E, or H, respectively. Right, meaning that, okay, if say X is F, then I take Y to be E. If X is H, then I take Y to be H as well. Okay, but then let me consider the following. The commutator of X tensor Ti with Y tensor T negative I. Okay, so this guy belongs to I, therefore since I is an ideal, the whole thing is in I. On the other hand, so computing this commutator just by all the rules that we introduced today gives me X, commutator of X with Y, plus, and I plus negative I is 0, so therefore this F, this central element also gives something in here. So, but what is this something is psi of xy, and psi of xy, according to the formula for psi, so is given by the following I. So this is not the imaginary unit, it's this I that I have here, xy c. So this is trace form. Okay. But let me see. So C is in H, and X and Y are chosen in such a way that they are also in H. So therefore, the whole thing is in H. So it's in I and it's in H, so it's in intersection. But intersection is trivial. Okay? So intersection is trivial. So therefore, we have that X with Y plus I x y c equals to 0. Very well. Okay, again, we have such a choice of x and y that this thing is some constant times h. Right? Commutator of E and F is H, commutator of F and E is H, commutator of H also H is 0, so just constant is 0 here. And C and H are linearly independent, so equality of this thing to 0 means that xy equals to 0. And also I x y equals to 0. Okay. Very well. So since again, by such choice, this thing is the trace form is of xy. You just can check it with such choice of x and y. It's not 0. Right? So therefore I is 0. So okay, so since I is 0, we have element x. So we have that I contains element x. Right? So therefore x cannot be h. Right? Because I intersects h trivially. Right? So therefore X cannot be H. But on the other hand, but then since X is not H, so we kind of get rid of this pair, but then commutator of E and F is H, it's not 0. Commutator of F and E is also, it's negative H, not 0. So it's a contradiction to the fact that X and Y should be 0. So therefore, so this is contradiction. To X and Y equals to 0. And so since we have contradiction, it means that I cannot be a non-zero ideal such that there's no non-zero ideal such that it intersects trivially with H. And so we proved part 3, and we proved the theorem. So finally, so we kind of we achieved our goals. We see that affine SL2 hat is the Kac-Moody Lie algebra, and now you can study generalization and understand easily everything about generalization. So you actually start with Cartan matrix of a simple Lie algebra, and add like one more row and one more column such that it is degenerate of yes, and so you will have the same generators like in simple Lie algebras, and one additional which you label usually by 0, and this 0 additional thing corresponds to the variable that you add in your loop algebra, in loosely speaking. Okay, and everything is proved in the same way. Also, these arguments that I gave you, they show why it is better to define Kac-Moody Lie algebra by forgetting about the cell relations, like hard cell relations, and just quotiening by this ideal, which in maximal, which intersects trivially with H. It's just much easier to use that to prove that something is Kac-Moody Lie algebra, rather than checking that there are no other relations than cell relations. Okay, so one last thing that I would wanted to say is that, okay, now having this root decomposition, one can ask which roots are imaginary and which roots are real. So this you can actually just check. So you can just take your roots and compute the form, right? So for example, you can compute what is the square of the form of delta with itself. Okay, and well, so delta, and this you also can check, is actually alpha 0 plus alpha 1. Okay, so this is alpha 0 plus alpha 1. So therefore, plugging it into this equation gives me alpha 0 with alpha 0 plus alpha 1 plus, well, of course, 2 alpha 0 alpha 1. Okay. So my Cartan generalized Cartan matrix is already symmetric, right? And so therefore, so remember that we introduced the following form on alpha I alpha j. It's a j I. So this are elements of Cartan matrix divided by d j. Right, and you can since Cartan matrix is already and so these are diagonal elements. So A is then D B, where B is symmetric and D J are diagonal elements of D. Okay, and since A is already symmetric, you can think of these as 1. So therefore, alpha I, alpha j is just A, J, I. So therefore, this one is 0, 0 element of Cartan matrix. So this is 2. So this is 1, 1 element of Cartan matrix. So this is also 2. And this is off-diagonal element of Cartan matrix, which is negative 2. So we have 2 plus 2 minus 4. This is 0. So therefore, delta with delta is 0. So therefore, all roots of this sort, k delta, are imaginary. And all roots so you can also compute what is alpha 1 plus k delta, right, with alpha 1 plus k delta. Well, I claim that this is actually alpha 1 with alpha 1. Right, because well, alpha 1 with delta, I can check. Okay, this is alpha 1 plus alpha 1 with alpha 0. This is 2. This is negative 2. So this is 0. And this one is 2. So this is greater or equal than 0. So all roots of this sort, or negative alpha 1 as well, if I put here, are real, and all roots of this sort are imaginary. Okay. Another interesting question that we unfortunately don't have time for is what is the Weyl group? What is here? So Weyl group, in this case, it is isomorphic to the Weyl group of SL2, which is just corresponding to one reflection, right, on a real line, and then semi-direct product with Z, and this Z corresponds to translations. So in Weyl group, it is now infinite. It is generated not only by reflection, by translations, and you just can see it just from the definition that we introduced for Kac-Moody Lie algebra, and just by hand it's so checkable on SL2.